Well, welcome everyone to this QISS seminar. Today we have the pleasure of welcoming Jessica Bavaresco from Sorbonne University and CNRS. She's a CNRS researcher in France. And she will talk to us about processes with indefinite causal order, specifically the quantum switch, and whether they can be deterministically simulated. So, Jessica, I pass it to you.
Thanks. Thanks a lot, Ognir, and thanks to the organizers for the invitation, the opportunity to present our work here today. So is it okay if I leave the slides like this? Because if I do real full screen, I lose my cursor and then I cannot point and I don't know how to.
It was just perfect because in any case, they don't occupy the entire screen. There was
Yeah,
this.
okay. So I'll do it like that. So then at least I can point. Okay, good. So yeah, so like Ognan said, I wanted to present this work today about kind of how hard it is to simulate the quantum switch using quantum circuits. So it's like standard quantum computational models. This is a work that was done in collaboration with mostly people who were at the time in the group of Miyamura at University of Tokyo. So my collaborators, my co-authors are Hilja Christiansen, who's now at the University of Montreal, Miyamura, Tatsuki Odake, Marco Tullio Quintino, who's also here at Sorbonne University, Philip Taranto, who's currently at the University of Manchester, and Satoshi Yoshida, also at the University of Tokyo. So at the time, we were all kind of either visiting or working in Miyamura's group. And to begin, so I thought I would start by saying a few words about the formalism of high order operations and point out the features of this formalism that we use extensively in this work. So I imagine that most people here are familiar with some aspects of causality and some aspects of indefinite causal order. So I apologize if this is a bit redundant, but it's just to make sure that kind of we're on the same page. So the formalism of quantum operations, we start, of course, with quantum states, right? This is how, in general quantum theory, in standard quantum theory, we talk about encoding data into quantum systems. I'm going to be using a lot this sort of quantum circuit-inspired notation and figures here. So, okay, we describe quantum states, or we describe our quantum data by quantum states, right? Which are some linear operator acting in a Hilbert space. Our functions are given by quantum channels. So these are functions that transform, let's say, data into data. So they transform quantum states into other quantum states. And in quantum theory, these are quantum gates or quantum channels. They are completely positive trace preserving maps. Okay, so not only, let's say, maybe quantum gates, when people hear quantum gates, they think more of only unitary channels, but in general, in quantum theory, any CPTP map is a valid function from states to states, right? So this would be considered sort of like the zeroth order object and the first order object. Then a second or higher order object would be a transformation, a function of a function. So we call them quantum processes in general. And these are objects that take a function as input and map it into another quantum function. So here in this formalism would be an object or a transformation that takes a quantum channel as input and transforms that into another quantum channel. And this is what we call a higher order operation. They're described by supermaps. And they're just, linear maps that transforms linear maps into other linear maps. Okay. So this formalism, and the way we're using it here now is kind of mostly coming from the tools and the techniques in some of these works. More recently, there has been a review and a tutorial paper from a year ago that's on the archive, which is kind of presenting and formalizing all of these things in a kind of language that we're using very close to what we use in this work. Of course, these are not the only ones, right? These are just a few examples. So in this formalism, two of the key features that we are using here is that one, higher order operations are very useful to describe quantum circuits, so like a standard quantum computing model. And also they allow us to formalize computations that go beyond the standard quantum circuit model. Okay, so the first aspect here, when we think, the number one, when we think of a transformation, not only now that maps, like in this example, one quantum channel into another quantum channel, but a high order transformation that takes many quantum channels as input, and we wanted to map it to another quantum channel. And we want this transformation to be described by a circuit, and we can see the output of the circuit as another effective channel, right? So I'm not thinking about putting any input states here yet. I'm just thinking of the circuit which had, let's say, these open slots, and now I plugged in different quantum channels into these open slots, and now I can see the whole thing as a new quantum channel, right? And whenever I want my transformation to be described as a circuit, I can use a higher order operation that people call a quantum comb or a sequential supermap, sequential superchannel to efficiently describe this transformation. So let's say I want to optimize over all transformations from some set of channels to a channel. If I want to do this in the quantum circuit formalism, I have to look at each bit, each part, each encoder in my quantum circuit and kind of optimize over them individually. And if you phrase the problem like this, there are no non-efficient methods of optimizing, right? But now what the higher order formalism tells me is that I can, without loss of generality, describe this quantum circuit as one operator, this C operator here. And this operator can be optimized using semi-definite programming, usually because it satisfies only, it's defined by a positivity constraint and some linear constraints. And then if my objective function that I want to optimize over is also linear, then I can do this with semi-definite program, which can be solved efficiently numerically. And also there's a lot of analytical techniques related to the theory of semi-definite programming that can be very useful. And then at the end of my computation, when I find the optimal quantum comb that implements my transformation, I am guaranteed that there exists a decomposition of this kind of abstract object back into a quantum circuit. And finding this decomposition is also easy. There are analytical constructions for this decomposition. So this allows me mathematically to simplify my problem a lot and solve it more efficiently. The second aspect that I mentioned is how high order operations, they allow us to go beyond the circuit model. And that's because if I consider now, let's say a transformation between two channels, say A and CB, into another channel, and I just want to say, well, the output of my transformation has to be a valid CPTP map, but I don't specify that I want this transformation to be implemented by a quantum circuit, then we'll find that there are more general such transformations that are what we call admissible. They're valid transformations for every input channels. The output will be a valid channel, and that they cannot be decomposed as quantum circuits. And these are the ones that we say that have an indefinite causal order. So this is how I'm kind of representing this here and saying that there are transformations that are more general than these quantum combs. And one example is the quantum switch, which I imagine you're probably familiar with. So the quantum switch is a transformation that maps two channels, here A and B, into another output channel. This output channel acts on two systems, a control system and a target system. And the order of this transformation is conditioned on the state of this control system. So if the control system is in state 0, then we have that the target system is sent first for channel A and then for channel B. And if it's in state 1, it's the other way around. First, the target system gets sent for channel B and then channel A. Then, of course, since my control system is a quantum system, I can set it to be in a superposition of 0 and 1, which would then allow me to see the target system as also being acted upon by these input channels A and B in a superposition of different orders. It's like a conditioned superposition, right? You can see this as entanglement between the state of the control and the order of the applications of the channels A and B, right? And okay, this is a very well-known and well-studied higher order transformation with indefinite causal order, which is the main topic, the one that's the main topic of this work. So formally, the way we define a quantum switch is the following, and it's been defined for the first time in this reference over here. So we're going to define the action of the switch by the cross decomposition of the output channel of the quantum switch, right? So we see that you have this higher order transformation, the switch. Once we plug in input channels A and B, now I have an effective channel out. And this channel has a causal composition, which is written here in the bottom, right? So this would be the state of the control coming here and the state of the target coming here. This is the causal composition of this channel. And each Krauss element can be written like this, as a function of the Krauss decomposition of the input channels A and B. So if AI, the AIs are the Krauss operators of channel A, and BJs are the Krauss operators of channel B, then the Krauss operator of the output channel can be written like this. So you can kind of see this idea again of like a superposition of A before B and B before A, conditioned on the state of the control. But it's a superposition of the Krauss elements of these channels, right? So this is how we formally define the quantum switch. So there have been many advantages, not only of the quantum switch, but of indefinite causal order, so of high order transformations that cannot be described as quantum circuits that people have found in the literature. And this is by no means an exhaustive list. These are only a few examples related to channel discrimination, estimation, metrology, arbitrary unitary transformations, and some computational advantages. But usually when people talk about advantages of the quantum switch or of indefinite causal order in general, they're comparing a transformation done by the quantum switch with a transformation done by a quantum circuit that acts on the same number of copies or the same number of queries of the input channels, which is of course a fair comparison, sorry. And then we say, well, there are transformations that I can do if I have the switch that I could not do if I had a quantum circuit acting on A and B. The question that we ask in this work is a little bit different. The question is, what if I had access to more copies of A and B? Could then I reproduce the transformation done by the quantum switch on arbitrary channels using this quantum circuit, using a quantum column? And this is when we start talking about this notion of simulation, right? Can I reproduce the action universally of this transformation by having a standard quantum computer, is a standard quantum circuit, and has access to multiple calls of these operations? We know some answers to this question, right? For example, we know that if the quantum circuit doing the simulation, sometimes here we call the simulator, if it has access to an infinite number of copies of the input channels, then it can simulate, right? It can simulate the quantum switch. So to simulate it is to prepare the same output channel that the switch would prepare given some inputs, right? So if I have infinitely many inputs, even if I don't know in principle what the input channels are, if I have access to infinitely many copies, I can just do process tomography and find the full classical description of these channels. And then since I know the classical description of the channels and I know what the quantum switch does, I can just prepare the output that the quantum switch would. So this problem is only interesting if I say I have access to a finite number of copies of the input channels, which is also like a reasonable physical assumption to make, right? That you don't have access to infinite resources in general. Another thing that we know is that you can do approximate simulation, and you can also do probabilistic simulation. And this has been shown already in the first paper that defined the quantum switch, that with some non-zero probability, even without extra copies, using post-selection, you can reproduce the action of the quantum switch. So this we know it's possible. And we also know that for some particular subsets of inputs, a simulation is possible, in particular for unitary channels, right? If the switch is acting on only 10 channels, and this we'll see in detail in a bit, then we know that we can reproduce its action. But we don't know at this point whether universal simulation is possible. So these are kind of like the rules of the problem that we're tackling. We want to find a simulation in terms of a quantum circuit that uses a finite number of calls of the input channels. We want it to be deterministic and exact, and we want it to be universal. And to impose this universality condition, we use the kind of model of black boxes, right? You kind of pretend that you're being given, let's say, by a referee, input channels A and B in a black box form. So you don't have any idea of their classical description. You don't have any idea of how they work. And you just have to plug them into your simulation. And without knowing what the input was, you have to make sure that the output of your high order transformation has to be exactly what the switch would do. So we want this to work for every channel. And then how we measure sort of the cost of the simulation is in terms of a notion of quantum query complexity. So we want to ask how many copies of channel A and how many copies of channel B do I need to deterministically and exact reproduce the action of the quantum switch? Okay. So this is the setting of the problem. Let's start talking about in the beginning, like how sort of non-trivial it is by analyzing a known universal simulation, which is the one I just mentioned that works for unitary channels. So, and this is also, so this simulation was already presented again in the first paper that defined the quantum switch. And it works on the following way. Take this circuit here where each of these gates are control swaps. And this is just a bit flip gate. So this circuit here, when I plug channel A, B, and another copy of A, I can see it now, the whole thing, the whole kind of box as one channel, right? The output channel of my circuit. And this channel here has this Krauss decomposition written the following way. So you can see that in general, it's not really the quantum switch, right? But if I take now A and B to be unitary channels, meaning that they only have one Krauss operator in their decomposition, and I plug this into here, now I see that actually, let's go for the circuit together. Maybe that makes it more easy. So here in this circuit, so this is the control. I need an auxiliary system, and this is the target, right? So if I start with my control state on state cat 0, then my target will just, well, the first control swap and the second control swap will not act. So it just goes straight for copy A, copy B. Now the control gets flipped. So now the control swap acts and I just escape for the top around the second copy. So the exit target here went through A first and then B. Now the control is on state cat 1. It's the other way around because these two first control swap gates, they will act. So I will first escape the first copy of A, and then the target will go for B. Now the second two control swaps don't act. So I go first for B and then for A and then out this line. And what happens in the auxiliary line is that I get the other copy of A coming out here. So this is how it looks like. This is the target state, output state here. This would be what acts on this auxiliary system. And this is what happens on the target system. So we see that I cannot just, since the Krauss operator of this extra copy of A that acts on the auxiliary system on this branch of the computation is different potentially from the one on this branch of the computation, I cannot just trace this out. Because it creates entanglement, and then what I get out is not going to be the same thing as the quantum switch. But in this particular case where I have only one Krauss operator to describe channels A and B because they're unitary, then this extra copy of A that acts on the auxiliary system does factor out. And when I trace it out, I get exactly what the quantum switch would do in unitary channels. So that's how you can do a simulation using only one extra copy of one of the channels for any dimension. You see that this, I didn't say anything about the dimension of the target system. So this is a kind of a constant cost of one extra query for any dimension. And I can reproduce the action of the quantum switch. But like we discussed already now a little bit, this doesn't work in general. So if I just trace out this auxiliary system here now, it will not give me the same thing as the action of the quantum switch. So the simulation doesn't work in general. And then the question is, okay, this circuit doesn't work, but could there be another circuit that does work? And what we find out is that it's not possible, at least not when you have one extra copy. So these are our two main results. The first one is that if I fix one copy of B, like I had in the example of this non-universal simulation before, and I have a number of copies of A, which is less than 2 to the power of n. And now n here is the number of qubits that channels A and B act on. So this is related to the dimension of the target system. Essentially, this is the dimension of the target system. So if I have a number of copies of A that is less than the dimension of the target system, then it's not possible to simulate the quantum switch. So for 1 qubit channels, if I have 2 copies of A and 1 copy of B, it's not possible to do this in general, for example. And if I have 10,000 dimensional system, then if I have 10,000 copies, it's also not possible. The other thing that we show, which we could now, of course, ask what happens if I have an extra copy of B, because this is quite constrained, right? I have a lot of copies of A, but still 1 copy of B. And turns out that this problem is much harder to tackle. I mean, this one was already hard, but generalizing to more copies of B is very complicated, and we could only do this using very different methods, and then only show in the case that you have 2 copies of A and 2 copies of B that this is not possible. So these results here in the bottom, this particular cases of 2 and 1 copies, 2 and 2, or 3 and 1 copies, we can show them using different techniques that, again, the simulation is not possible, but here we can also talk a bit more about robustness, because we can upper bound the probability of success, show that it's strictly less than 1, and we can also talk about approximate simulations and show that even in the approximate case, the simulation is very hard. So we break it down in kind of these 2 cases. So let's take a bit of a look in the details of this theorem here, the one where we have only 1 copy of B. So the interesting thing about this theorem is that first, it's more general than just saying that the quantum switch cannot be simulated by quantum circuits, because we actually consider a class of simulators that is a bit more general than quantum circuits. And these are quantum circuits with classically controlled causal order. So, or quantum circuits with classical control. So this is a definition from this paper here. And these are quantum circuits that can have a non-fixed order. They can even have a dynamical order, but still it's controlled by a classical system. So in a way, it's still like a causal order. And we allow the simulator to do that, to have access to a classical control of orders, and we still show that a simulation is not possible with this number of copies. And the assumptions are not even universality. We don't have to require universality to show that the simulation doesn't exist. In fact, we say that B can be only a unitary channel, just in the case where the simulation exists. And the A channels are all convex combinations of unitary channels. So it means that this circuit from before, this scenario here, even though if I keep B as a unitary and I say, now I don't want A to be a unitary, but I want it to be potentially a convex combination of different unitaries. So you just throw a coin each time you prepare a different unitary. This is already sufficient for us to show this separation in query complexity, that if you have up to 2 to the n copies of A, you cannot simulate even using a classical control of orders. Okay, so these are kind of like the details of this theorem. And the proof is quite technical, so I think there's not enough time to kind of go through the details here. But the second part now, some more details on the second part, is a bit what I mentioned before. Like for these examples of this number of copies, we studied probabilistic and approximate simulations, and we show how the error and how the probability behaves. So to talk about probabilistic simulations, we do the following. So now we accept, so probabilistic, I mean, in terms of probabilistic heralded. So post-selection, with post-selecting on a specific outcome, you know that you have exactly the simulation that you want. And these can be implemented by quantum circuits that prepare an extra system, and then you make a measurement, a 2-outcome measurement that represents either success or failure. So if it's success, you know that you have exactly the transformation you want. And if it's failure, you get something else that doesn't matter. So if we show, of course, that the maximum probability of success in a certain scenario is less than 1, it means that the deterministic simulation is impossible. And that's what we do here. Because we're going to tackle this using the computer for some parts of the proof, we also want to reduce the dimension of our problem. So if we require simulation to work only in the restricted case, and we show, the question now is just, I want to simulate the switch, the action of the switch on all channels, only for the control state, in state cat plus, and only for the target state cat 0. And for moreover, we trace out, we discard in the end, the output target state. So this is an equation here now that's comparing 2 quantum states. And when I see, can I simulate the action of the switch on the output control system using a quantum circuit? And of course, if I show that this restricted simulation is not possible, it means that the more general simulation is also not possible, which is what we do. And finally, instead of saying that I want my simulation to work for every quantum channel, I say that I want it to work for a basis for a set of operators that form a basis for the space that is spanned by k copies of a channel. And this is equivalent. Here, there's no loss of generality. If I show the maximum probability that simulating the action of the switch on this basis, it's the exact same as simulating the action of the switch on every CPTP map. So this is just a technique to go from this kind of infinitely many constraints to a finite number of constraints that then allows us to solve this problem using semi-indefinite programming, which is what we do. So asking the maximum probability of success of a simulation can be phrased in terms of an SDP, which is this SDP here. And any feasible point in this problem will give us a lower bound on the probability of success. Which means, because of the duality of semi-definite programs, that there exists a dual problem, which is this one here, and any feasible point in this problem will give me an upper bound of the probability of success. And that's what we want, right? We want to show the probability is strictly less than a certain amount that is less than 1. So what we do is we solve the dual problem, and we find, well, because this problem satisfies strong duality, if you solve it with the computer, in principle, you get the exact probability of success. But ultimately, we don't want to rely on the computer to do this. So what we do is develop a method of computer-assisted proofs that takes the numerical solution of this SDP, treats it as an ansatz, and uses it to build a proper formal mathematical proof. So this technique, the way it works is by expressing a valid solution, which is a valid upper bound for our problem, in terms of only rational numbers, so that we're not susceptible to any floating point errors. So we run the SDP using floating point numbers, as anyone would in the computer. But then instead of treating the output as the solution, we treat it as an ansatz. And then we rewrite it in terms, approximately, in terms of rational numbers for an ansatz that exactly satisfy all the constraints of my problems, and that I can check or prove that these constraints are satisfied without at any point relying on floating point arithmetics. And then at the end, well, this will not be my optimal solution, but will give me some upper bound on my solution, which for us is enough to show that this upper bound is less than 1. So these are the probabilities that we get at the end after we do this, we apply this method. So here we have the number of copies of A on the left and the number of copies of B on the right. This is the order that the quantum circuit is acting on the channels. And it makes a difference, right? You can see that in the probability of success, it makes a difference if I'm using the order AAB or ABA. In fact, even for unitary channels, you can simulate with probability 1 if you have the order ABA, but if it's AAB or BAA, you cannot simulate with probability 1. So we look at all possible inequivalent orders for a given number of copies of A and B, and then we show all these upper bounds that are all significantly less than 1. So even the probabilistic scenario, there is a limitation to how well you can simulate the quantum switch, even with access to a higher number of copies. The only problem is that we are limited then by the computational power to compute these SDPs in the first place, so we cannot go higher than 2 copies of each. And then, so the last thing is the approximate simulation. Right now, we want to combine probabilistic simulations with approximate simulation as well. In this case, we say the following: I accept that my simulation is successful if with a certain probability, it doesn't prepare necessarily the output of the quantum switch, but something that is epsilon close to the output of the quantum switch. So if it's within a certain distance, I still accept as a successful simulation. And we want to show that still it's not possible to get epsilon close with probability 1. We have to sacrifice both in accuracy and in probability to be able to simulate the switch. So first, just to compare, this is the case with no extra copies. So just 1 copy of A and 1 copy of B. And we see that even as we relax epsilon, sorry, so this is the Choi operator fidelity. This is what this quantity here is. So it's the fidelity between the Choi operator of the quantum switch and of the output of the simulation, which is approximately the quantum switch. Okay, it's bounded by 1 minus epsilon in fidelity. So then here we fix different values for epsilon. So we're increasing the error and kind of making the approximation more and more relaxed. And then we see that the probability of success of achieving this error increases. However, it takes quite a bit of error for the probability for the simulation to be possible deterministically. And here we see that allowing the simulator to have access to classical control of orders doesn't improve over a fixed order. Now, when we go to the case of 1 extra copy of A, so 2 copies of channel A and 1 copy of channel B, we have to look at all three possible orders, and we also compare the simulation with classical control of orders. And when we do classical control of orders, it's kind of automatically optimized over all possible orders and combinations of orders and dynamical orders. So we just have one curve to analyze. And here we see again that as we increase the epsilon, it takes quite a bit of time for the simulation to be possible. Well, quite a bit of error for the simulation to be possible deterministically. And we see also some kind of interesting behaviors is that the optimal order of simulation changes depending on how much error you allow. And that for a while, there is no advantage of classical control over the kind of best possible order. But after some point, when we have kind of enough error in our simulation, we get that classical control can bring an advantage in the probability of success of the simulation. And this seems to be related. So this S here, the target switch, is the restricted switch, which is the one that has the control input state and control target state fixed. So again, we do this to reduce the size, the dimension of our problem. And showing the hardness of simulating this particular problem means it can only be harder in the general form, right? So here, the control, what this means is that here, the input states are fixed. And for the quantum switch, when the control input state is fixed, it has no dynamical order. But as we relax the simulation and we allow this epsilon to grow, we may be including operations around the switch that do have dynamic order. And then it seems that that's why classical control can help, because it can help reproduce this dynamical order of the high order objects that are epsilon 1 minus epsilon fidelity close to the quantum switch. Yes, I think this is the main message here. Unfortunately, again, we cannot do this plot. We didn't manage to run this plot for the case of 2 copies of A and 2 copies of B. And this is all for qubits, right? All of this, all this sort of numerical part was done for qubit channels. We have a few other additional results on the paper that I'm not going to show here, but if anyone is interested, so we also show an explicit circuit simulation that is non-universal, that is a generalization of the one we saw. So we saw from the original paper that defined the switch, the simulation that works for unitary channels. We show that a very similar version of that circuit also works to simulate unitary channels when the switch only acts on part of the unitary channel. Which is, we also study a little bit more the case where the quantum switch is acting on unitary channels, because we find that if you're not in the specific order of A, B, A, the simulation is not possible. So we also computed using these computer-assisted proof methods, the maximum upper bounds and the maximum probability of simulating the action of the quantum switch on unitary channels for different orders. And when you have 2 copies of each or 3 copies of one and 1 copy of the other. And finally, we also looked at the non-trivial case of the action of the switch on identical channels. Because even when the channel A is equal to channel B and you want the simulation only to work on AA, the action of the switch, if A is not unitary, is non-trivial. And then we show that up to 4 copies, it's still not possible to simulate the action of the switch deterministically, even when in the restricted case when A is equal to B. And finally, we have a discussion in the paper about also how to formalize what a simulation means for the action of the quantum switch on quantum instruments and on these extended channels, and also discussions on the failure of a simulation for the Stein spring dilations of quantum channels. And if I can do a little bit of advertisement, if you're interested in problems related to purification and Stein spring dilations, in the next couple of weeks, we are planning on put on the archive, together with Zoe Garcia del Toro, a PhD student working with me, a paper about no-go theorems for universal quantum purification machines, which in the end are kind of related as to why, even for Stein spring dilations of quantum channels, we cannot necessarily simulate the quantum switch so easily. And this is it for our main results. So as a summary, we showed that for a certain number of copies of the quantum a certain number of copies of the input channels, you cannot simulate the switch. I guess most notably is that even if you have a number of copies of channel A that go exponentially with the number of qubits that channel A is acting on, as long as you only have one copy of the channel B, it's still not possible to simulate the switch. And it's, of course, not clear how far we can generalize it. I think after working on this problem for quite a while, I believe even if you have, an exponential number of copies of the channel B and potentially even in any finite number of copies of A and B, it's not possible to simulate the action of the switch exactly and deterministically, but this is still very much an open problem. And we also analyze the robustness for these three particular cases here in terms of probability and of probability of success and of simulation error. It would, of course, be very nice to understand a little bit more about the robustness of these more general scenarios. And in general, how it scales, right? Because we have computed P and epsilon for these specific cases, but we don't understand very well yet how the scaling of these quantities goes with the number of copies of A and B. And more generally, also, we'd like to know, what about other high-order transformations? The quantum switch is only one of them. And it would be interesting to see if there is sort of a way to categorize and understand different high-order operations with indefinite causal order based on the hardness of their simulation. So I think this is some of the kind of immediate open questions of our work. And then that's it. Thank you very much for listening.
Thank you, Jessica. Thank you for this very clear presentation. There are some claps in the chat. I would like to start with a question. This result is, I think, from a quantum information theoretic point of view, it's a very, very well posed problem and very clear and somehow definitive result. But I wonder about the implications of it for more, let's say, a bit more foundational questions that have to do with the interpretation of these higher order processes. And in particular, we've been very interested in, this community has been very interested in processes with indefinite causal order because they are speculated to be relevant, maybe also in regimes where both the general relativity and quantum theory are relevant. And in particular, there is this proposal for the gravitational quantum switch, which is a kind of a hypothetical realization of this type of process in a gravitational scenario where the order between two events is switched by exploiting time dilation, gravitational time dilation, which somehow happens in superposition, controlled by the position of different masses. And I somehow, when I hear this result, I feel that it tells us something very important, potentially, about even conceptually understanding, the realizability of this type of theoretical concepts in physics. But I'm not able to put my finger on it precisely. And I was wondering whether you have yourself thought about this. Maybe to make a little bit of a connection to something I'm sure you know about. We have these works on realizing processes on time delocalized subsystems. So this one idea is that you could realize the quantum switch, for example, in a certain sense within standard quantum mechanics, but using so-called time delocalized operations or systems. Essentially, it's an interpretation of certain type of experiments that people have been doing since the start of these ideas, which give us a kind of real understanding of these experiments from a different point of view, different factorization of the Hilbert space. And then now this result of yours somehow seems to put this in some tension with this type of interpretation in your result, I sense, although it's not precise. And I wonder, do you have any thoughts about that?
Yeah, I think so. Our perspective in this work is to compare the quantum switch with what is like a quantum computer could do, like an all-powerful quantum computer that can implement any quantum circuit. And then, so the question is a bit like, is the quantum switch within reach of a standard quantum computer? Or is this something that kind of goes beyond these quantum computational models and that requires more resources than what a quantum computer can do? So this is kind of the comparison. Let's say if you are given something that is truly the quantum switch, and you want to simulate that with a quantum computer, the message is kind of like, well, you're not going to be able to. Of course, we don't prove this in full generality, but let's assume for a second we could have done that we managed to prove this in full generality. It's saying that you cannot reproduce this full computational power using a quantum computer. If you're in comparison to this time delocalized systems, I think, and okay, maybe one more comment is that you cannot reproduce this with a quantum computer when it's given access to this sort of black box queries of the input channels, right? So if the quantum computer is given access to the Stein spring dilation of any channel, but it's already given to the computer in that form, so you're always only getting unitary channels as input, then the quantum computer can do the same thing as the quantum switch. What the quantum computer cannot do is take a black box channel and transform it into the Stein spring dilation. I think it's similar with the time delocalized systems. If you're given black box access to quantum channels to a quantum computer, it cannot transform these black box queries into the time delocalized implementation. But if you're given the time delocalized implementation of the quantum channels, then, and you give that to the quantum computer, then you would be able to. I think this is the only thing we can say about this question from this perspective is kind of about the resources. What you give to the quantum, you give some resource to the quantum computer, and then you ask. And I'm saying quantum computer because we're using quantum circuits, right? And that's like a universal computational model. So I feel like I think we are allowed to think about it that way. So if you're giving the quantum computer some resource, it can do the switch. If you're giving another resource, it cannot do the switch. And in this way, we try to gauge how good would it be to actually get the switch, right? How much more you could do with that compared to a quantum computer. I feel like that's the only things that we can say in the end. And then when it comes to, I think the interpretation of the experiments is about understanding what are the resources being given to the experimental implementations, right? Are the channels being given to the experiments already in their time delocalized form or not? Are they being given already in their unitary dilation form or not? Right? And then we can ask whether or not this, whatever is being done by the experiment could or not be reproduced by a quantum circuit, having access to the same resources. I don't know if that
Right.
answers.
Yes, I think this is correct. Somehow, what you say that the form in which the black boxes are given. And this, I wonder how important it is actually to be given the actual Stein spring dilation. Or do you, I mean, because we could also conceptualize the notion of being given maybe a time delocalized version of a channel, still without access to the actual Stein
Mhm.
spring dilation. What
From
do
what I
we?
understand, if you are given the time delocalized version, then having access to time delocalized implementation of the channels plus quantum circuit, it's possible to do the switch, right?
Yes, I suppose. But
But I'm not 100% sure. That's kind of what I understood, but I could
mhm.
be missing something.
And yeah, and in a gravitational setting, that's very somehow it's different, but at the same time, it seems to be isomorphic to a time delocalized implementation.
Mm-hmm.
Although, well, it all appears, but we don't know. And there, it seems somehow more natural that you are given the channel in a somehow local, maybe in a local inertial frame or something like that, where you of course, in the context of the gravitational switch, one needs to always make some physical assumptions, additional physical assumptions in order to define the setting and the rules of the game in order to appreciate that it is interesting, because otherwise you can always maybe take a more external point of view and you can see everything as a, let's say, more standard implementation of the switch. But let's say there maybe there is this natural notion that we can imagine these locally inertial frames, and in these frames, so let's say standard physics holds, and therefore we have a good notion of what it means to use or probe a black box. But yeah, if we want to give this concept like somehow without any specific reference to some physical assumptions like local time, local inertiality, or whatever, do we know how to even phrase the notion of having access to a black box channel? I wonder. I mean, mathematically, we can just use it in our calculations, but physically speaking, what do we imagine when we say that we are given a black box?
You mean in this kind of gravitational sense,
Or,
or
abstractly speaking, typically I would imagine maybe that I press a button and the channel is applied or something like that.
yeah.
But this again, I put it already in a very concrete physical, temporal idea that I have about using channels. But do you think, I don't know, that there could be a way of giving a very universal notion of accessing
Yeah.
black box channels? Yeah.
The way I see it personally, and I think maybe it's because I'm kind of drawing from Bell locality, is seeing a black box as like an operation that you don't have the classical description of. So in our case here particular, which I think is not exactly what you're asking, but in our case of simulation, it means that the oops, it means that this operation C cannot depend on A and B. It has to be the same C for every A and B. That's what it means to be given A and B as a black box. It means you don't know beforehand what A and B is going to be. And then you have to make the simulation, prepare the circuit before you get access to A and B. And then, of course, in practice, if you're doing something on the lab, you always know more or less what you're trying to do or what you are implementing. But it's just that the circuit itself cannot depend on that classical description or even, let's say, quantum information, right? Because maybe you can even have partial quantum information about the channel. Like you can have access to a quantum state that you know is an eigenstate of a certain unitary or something like this. And that's already extra knowledge. And that you can use that quantum information to feed into your circuit and let the circuit depend on this information, right? So here I see it very much as like what is given to you in terms of a black box is just like what is not given to you. And what is not given to you is any description of any classical information about what's going on in the channel. And you have to make your setup regardless of that. Like you don't know anything and you just have to prepare in advance your setup. And now the inputs come.
Mhm. Yeah, so this makes actually a lot of sense, and now it makes me think that maybe it's the most natural way of defining this is by two players in a sense. Like you can imagine that the player, the referee, is preparing these black boxes, and that referee, however, I mean, physically, if you want to imagine somebody preparing time delocalized operations, that referee would, as far as I know, would need to use the dilations, right? But it could still be that you are not given access to the purifying systems.
Yeah.
And in that sense, that referee, like you can prepare a setup and the referee might plug in, so to say, in your slots, the delocalized operations. I guess you would need to prepare delocalized slots, in the way you do. And then somehow there should be this interface between the two different preparations. But yeah, in that sense, maybe it makes sense to discuss a delocalized channel being given to you, even without you having access to the purifying system.
Mm-hmm. Mm-hmm.
Perhaps, okay, I am, that is not a claim because I'm not totally sure that I see all these connections, but yeah. For somehow, yeah. Um, and about physics, I mean, do you think that this like taking it maybe a little bit more speculative, this type of computational complexity separation, let's call it, could it provide us some insights in your view about maybe if we assume that this type of phenomena occur in a quantum gravitational scenario, as it has been proposed? And do you think this could be some sort of test or provide us some insights into, the power of computing of physics?
I think so. I think so. If let's say we can prove that with no finite number of copies, you can simulate a quantum switch using a quantum circuit. I think there are like two different ways that you can take this. One is you can say that the switch is giving you some kind of absurd, implausible computational power, and therefore it should not exist.
Mm.
But this is not something that you can prove, right? You can just say, well, it would be weird if it existed, right? Kind of like, again, going back to Bell non-locality, it's kind of like a PR box, right? So a PR box we know is a set of correlations that cannot be done by quantum theory in a Bell scenario. So like with space, like separated parties, you cannot produce PR correlations. But what is it to say that like there is no other theory in which it's possible to do PR correlations? And then I think the way the community sees is that, well, if I had a PR box, I could trivialize communication complexity. That's one of the results. And we think it would be weird to trivialize communication complexity. So we kind of collectively agree, well, it would also be weird to have a PR box. Maybe this thing doesn't exist. But you can ultimately not prove anything, right? Here, I think it's less weird because the switch, we can do the switch approximately, and we can do the switch probabilistically, right? And we can potentially get very close to doing it with lots and lots of copies. So it's not like an insane, absurd, like in this kind of approximate setting, the query complexity will never be infinite. So it's not completely unimaginable, but it could be that still it's very, very high. And then you could either take that as well, maybe distinction doesn't exist, or maybe there's some other physics out there that can still take care of it and can still do it. And maybe in the gravitational scenarios, it's still possible, and this would bring, and then you can interpret it as like, well, it would be really good because then it will give us a lot of computational power, right? But until somebody goes and makes it, we will not know, I think, what is the physical implication, right? I think you can only speculate as to what the consequences of it existing would be. And that's kind of what we're trying to gauge here is the ultimate power, computational power that the switch could give us, and what would be the cost of reproducing it with the physics that we already know for sure.
Mhm.
Yeah, it goes both ways in the end. Like it's you can either be very happy and think, well, the switch is going to be great, or think, no, it cannot be done because it would be too good to be true. I don't know.
Yeah. I actually have a follow-up regarding computational power, but I just wanted to ask in case any of the participants wanted to comment or ask anything in relation to this, and maybe the gravitational questions, because there are some experts here on the gravitational switch. You can raise a hand if you like in the chat. In any case, I wanted to follow up on the computational power, and now what I find very exciting about your work is this fact that you pose the question, you define a certain notion of computational complexity that I think is very important somehow, because it is really the right way to compare, to talk about this, the advantages of indefinite causal order for possible computations and so forth, because it's the very natural notion somehow, but at the same time, it is also a bit different from traditional notions of computational complexity, or at least those that are most commonly used. And so I was wondering if, like most commonly, we can talk about black boxes. There's one thing. We can be given a problem in the form of a black box, but typically we are given a problem. If we're not in the Oracle model, we're given a problem as essentially a mathematical function that we need to compute really on a given input, and which is a completely mathematical problem with classical computation. Whereas here, we are given somehow the input, the task, in some form of black box, which is itself a physical operation. And then we're asking, how can I simulate this? So the input and the output of that computation is a physical thing. And I wonder, how do you think this result could be somehow, maybe through some manipulation or some additional idea, be taken to realize some other more traditional notion of computational advantage?
Yeah. Yeah, no, this is a really good question, and I don't know. So the notion we're using here for like computational complexity is query complexity, right? Quantum query complexity. And the reason we're doing that is because it's kind of the only one that we know how, at least that we, the authors of this paper, know how to formalize it, right? I agree with you completely. That's not the most satisfying one in a sense, because we want to talk about actual computational complexity in terms of computational time, right? Because that's ultimately how we want to compare, let's say, a quantum computer with a classical computer. We would also like to compare a higher order quantum computer with a standard quantum computer using computational time, perhaps. But the problem is that this problem is defined with the inputs being these oracles, being these channels, right?
Mhm.
And we have this circuit or this high order transformation, these open slots. And the moment that we're not allowed to change what's inside the slot anymore, the moment we plug a channel in, and now we run the computation, this is now, there's no indefinite causal order to speak of anymore, right? From the moment you close the slots, this is just a quantum channel. And the quantum channel is just like, okay, it's the circuit now, no matter if I had the switch or whatever I had, from the moment that I put these channels here, this just becomes a quantum channel. And this quantum channel can always be done with a quantum circuit for that input. So if we don't want to talk about query complexity, about how many calls to these channels, I want to say, no, I already plugged in all the channels. Now I want to understand how long it takes for my computation to run. I don't know how to compare these different resources, the circuit from the switch and the switch. And I don't know how to formalize it in a way that doesn't have to talk about queries and can go back to like a more fundamental notion, like you said, like you have a function, you want to implement this function, what's the cost of implementing this function? It's something I think really important as a sort of field for us to figure out it, but I don't have any contribution right now, unfortunately.
Mhm. That's fair. It's certainly not an obvious question. I mean, the question may be obvious, but the answer certainly not. Yeah. Okay. Well, thank you, Jessica, for this nice seminar. I don't see any other questions, so I think it's we can wrap
Okay.
it up here. Did I hear something? Ah, okay.
Bye.
Goodbye, everybody.
Thank you so much, Agnes. Thanks, everyone.
Ciao.